Now, we have a 25,000 pound engine. However, depending on the size of the aircraft that it's fitted to, obviously, if it's on a 319, it only requires 22,000 pounds of thrust. Whereas if it's on a 321, it requires 33,000 pounds of thrust. Okay. It's the same engine. And all we do is we just tweak it through the FedEx. We can doctor. Yeah, we can doctor the output, how much pounds of thrust it does, although it's the same engine, by sucking in more air, compressing more air, and igniting more air at a higher temperature or whatever, and producing more thrust. Okay, so that's possible with the same engine. So, for example, if you took an engine off a 320 and next week you're fitting it to a 321, you also have to tell the engine, I'm fitting you now to a 321, and your engine now has to produce thrust of 33,000 pounds as opposed to 27,000 pounds that you were producing last week. Okay, so that's all done by pin programming and by the engineering, the maintenance actually, when they change the engine. You have to tell it what aircraft model you're fitting it to so that its brain, the EC or the FedEx, can think accordingly. All right, so different variants, different power. Obviously, you can fit a 33,000 pound on a 319, but it will be complete waste of energy, complete waste of fuel, and you want to not stress these engines unnecessarily. The engines itself, so the what we call the power plant which is the installation of it, includes the engine inlet, the exhaust, the fan cowls and the reverser assemblies in two halves. These two, and these are the fan cowls. The pylon connects the engine to the wing, and then the engine is attached to the pylon by forward and aft mounts. So the aft mount here, the aft mount here, and the forward mount here. It's really hard to do a component locations on one picture, but the general layout of the engine. So if you start from front to back, you have the different modules. So you have what they call the LP module, which is the low power module. So we have the fan. So this section would be called the fan and booster section, which is the fan itself, which is what you see when you look at the engine head on, with the LP compressor. And then you have the high pressure system, where the air really gets compressed and chopped and chopped and chopped and chopped and reaches enormous temperatures and pressures. And then it gets pushed back into this area here. Sorry, this area here, which is the combustor, where it gets ignited. Okay, and reaches 1800 degrees Celsius and gets pushed aft. The hot air gets pushed aft, which turns the turbine here, the LP turbine, and gets expelled. And the aft moment here causes the aircraft or the engine to pull or push or whatever it is, the aircraft it's attached to forward. We also, on this, attach an accessory drive to the gearbox, and the rotating motion of the engine can also, through this gearbox, operate other rotating things like generators, hydraulic pumps, oil pumps, etc., etc. If you want to look at it in a schematic way, so we have two shafts, two concentric shafts. So one is turning inside the other one like this. And you have the LP LP section on one shaft. So the LP compressor will be connected to the LB turbine, and the HP compressor will be connected to the HP turbine, and they're turning at different speeds for different purposes. And between these two shafts, I have to have bearings, which I lubricate. Okay, so I have a massive rotating washing machine going round, okay, on two shafts. So I have bearings at different sections, which I need to cool. So I cool with pressurized oil. So I push oil in under pressure to seal it all and make it tight, airtight as well. And I use oil and sometimes air pressure to cool these areas which get extremely hot, especially this one here. This is bearing number 4 is in the combustion chamber, and this is subject to enormous heat, so needs to be working all the time. In fact, bearing number 4 has its separate cooling system, okay, to keep it at the right temperature. And then you have the other bearings 1 to 5, okay, which can be rollers or ball bearings, depending on where they're located, to do their job of lubricating the whole system. Over here we have the HP rotor section and the combustion chamber. So the air comes in, it's really high compressed now, and this is where it gets ignited. Okay, and then goes to the HP turbine. The HP turbine will take in this heat and convert it to kinetic energy. So according to whoever said it, can't remember now, that energy can neither be created nor destroyed. So we're converting all the time. We're converting one form of energy to another. We're converting here potential energy, compressing, explodingly igniting it, converting it to heat energy, and then converting it from heat energy to kinetic energy. When the kinetic energy moves aft, it then meets the cold air, the hot temperature, kinetic energy. When it reaches the cold air outside of it, it forms another form of energy, which is noise. Yeah. Which is a part of it, but the majority of the energy is kinetic energy, which is the moment force to push this thing forward and create thrust. So the accessory gearbox is connected by a shaft here. So we have a rotating engine here. It's rotating at, I don't know, whatever, 1,000 RPM. And the shaft here is connected to this accessory gearbox, which is bolted on. This is it. It's not on the underside. It's around about, after looking forward, it's around about 7 o'clock position, where all the components are attached to. Okay, it's connected by what they call a angle gearbox. Okay, takes it away from the engine, the rotation of the shaft through this angle gearbox to the actual accessory gearbox here. The heart of the system is, we said, is the FEDEC. Okay, the FEDEC is the full authority digital engine control. It was a big thing in the 80s and even in the 70s when 747s started getting all these fancy computers for the engines, which were all manual beforehand. Now your basic $20,000 car has an EEC in it, or an ECU. and controls how much fuel or fuel injectors. The fuel injectors were the first fuel injected engines were the first indication that cars were also going the FedEx route, that were being the fuel was being controlled, how much fuel was going into the engine, A, for fuel efficiency, and B, for power. Aircraft have been doing this now for several years on a larger scale, and that's what the EEC does. The EEC controls how much fuel goes into the engine to produce the required power by the thrust levers, and how much how that fuel is controlled in an effective way, and also how the power is managed in an effective way. And since it's a computer and it's got a brain, we might as well throw in, let it control the thrust at all settings, let it control the starting, let it control the all the different other functions of the engine need to happen. Let it do it, because it's a computer and it's definitely more accurate than a human. Okay, it monitors several things, monitors the air and pressure at different sections of the engine. So the P2, T2 at the inlet, the P3 and the T3 is the pressure at the burner, the combustion chamber, so to speak. Okay, it monitors the P5, which is the pressure at the outlet. On this engine, because it's an EPA engine, I need pressure in the inlet, P2, versus pressure at the outlet, P5, to give me an EPA figure. Okay, engine pressure ratio. And I need the EGT for the temperature at the exhaust. I've got T2 and the inlet and T5. I use temperature for N1 indications, and I use pressure for EPA indications. So this engine, although it's an EPA engine, the EPA is displayed. It has a default mode going to N1, so I also need the temperature to be monitored as well at all times. It monitors my fuel flow for obvious reasons. It monitors the temperature of the oil. It monitors the temperature of the fuel. And it then tells other systems, hey, you need to do this, or it switches on other systems for protections. It also meters my fuel. It meters my fuel and opens the relative valves and things. Some valves are used as muscle pressure to open, I don't know, active clearance control and boost the bleed valves and God knows what. So it monitors how much fuel pressure must be used to go in the combustion chamber for burning, for thrust, and also how much muscle pressure must go into these components, which are used as pistons, to operate certain valves and certain items. Okay, and I also have feedback from other pressures and temperatures to determine certain functions of the engine. The EC also controls the thrust reverser, when the thrust reverser should be deployed, when is very important, on the ground only, okay, and under what conditions it should be deployed, how much it should be deployed, how long it should be deployed, and how all these different functions. I also have a heat management system, which I won't elaborate a lot on, but what happens is the engine, the fuel that comes out of the wings is relatively cold. So I need to heat it up, okay, before I put it through the engines. So I have a heat management system by passing it through the hot oil. So I have a fuel cooled oil cooler and all these different acronyms for different devices that pass the cold fuel through next to the hot oil and therefore heat the fuel up. And by heating the fuel up to put it through the combustion chamber effectively, I'm also cooling the oil down that's getting hot because of its lubrication functions. And that's part of the heat management system. And it's all monitored via the EEC, via the FedEx, via the computer, of the engine. So the EC, because it's a very important box, has two channels, channel A and channel B. In 99% of the cases, all the items, the channel A monitors, channel B monitors as well, in an identical manner. So every component that's sending information to the FEDEC has two channels, one component or one bit of information going to channel A and the identical information going to channel B. Okay. All of that information is via an engine interface unit. Okay. And the engine interface unit is a box that takes all this information. It's exactly what it is. It's an engine interface unit. It interfaces the aircraft systems to the engine. Okay. And it gives the FEDEC all the information, what it needs to make decisions. Okay. Now, all 100% of the information in the EIU is transmitted from the aircraft by the EIU to the FEDEC. All 100% of the communication between the EIU and the FEDEC is ARINC 429, this yellow data bus. However, some of the information between the aircraft and the engine, okay, is direct communication, either through analog or discrete signals. Okay, but anything that goes through the EIU is a data link, ARINC 429. Now you're going to say, oh yeah, but what happens if this channel A goes? I only get half the information. I always get the information from the other one, and these informations are always these channels A and B are always this is a data link, a cross communication data link between channel A and channel B. They are always communicating with each other. So even if I lost the whole FEDEC channel, channel B, okay, channel A is self-sufficient to be able to control everything on that engine. All right. Separate to these units, I also have the vibrations are not monitored by the EEC or the FEDEC, and the vibrations are taken, the signals are taken by analog to the another computer called the EVMU, the Engine Vibration and Monitoring Unit, which then puts up indications on the ECAM or on the engine display for the pilot to monitor and take the necessary action if there is excessive vibrations. So here we have a typical thrust reverser, what the engine, what the EEC and the EIU, how they interface with each other for an engine control. Typical thrust reverser system where the EIU is the interface, the EEC, the on-side EEC. Okay, so this one is in the avionics bay. This EEC is actually on the engine, the FEDEC. Okay, and it's showing us here the reverser system for the green hydraulic supply. So the green hydraulic supply will imply, if it's green, it's number one, it's the left engine. And it's telling us that the yellow hydraulic supply would be available if it was the number two engine, and the circuit would be identical. It's just that all these colors would be yellow. Not in real life. The hydraulic color is the same, but in this diagram, you'd have green to indicate system number one or engine number one, and yellow to indicate the right-hand engine for system number two. Okay, so the EEC has to then decide, okay, when this deploy signal comes from the throttle control lever, okay, it has to first be decided if we can deploy. Okay, all right. So captain has pulled the thrust reversers. Can we deploy? If the inhibition relay switch is made, okay, then this enables hydraulics to be moved to the thrust reversing actuators, and the actuators will move. Okay. So this HCU is used there to inhibit hydraulic supply going to the actuators. The engine is producing the on-side. Each engine has its own engine-driven pump, hydraulic pump. So it's producing hydraulics all the time, and its main purpose in life is to operate some flight controls. But when the reverse is on, here's my chance of my on-side hydraulic pump is going to feed my reversers only if the HCU, the hydraulic control unit, this inhibition relay allows it, because the provisos have been met. Okay, and we can deploy. The EEC decides whether we deploy if this relay is made, or when we stow. So the EEC commands these actuators to move in one direction to deploy, or in the other direction to stow. Okay, the actual command comes from the EIU into the inhibition relay, and other factors also: radio altitude, the air weight on wheels, the systems that ensure that the reversers can only be deployed on the ground. Now you're going to say, what the hell is this thing doing here? This is a spoiler elevator computer. What has that got to do with the reversers? Well, remember, guys, that the ground spoilers are used to decelerate the aircraft. Do you remember that? So when we're in reverse, the spoiler elevator computers also get a command that once the signal for a successful deployment is made, that we actually also automatically, the ground spoilers are also extended to do this function for us automatically if the hydraulic is there. All right, here's just a picture of what a thrust reverser looks in its stowed condition. Okay, so in flight or even on the ground with the engines, with the thrust reversers stowed, all the air comes in through the engine, whether it's the bypass or through the core, and once ignited and gets expelled through here. When we land and the reversers are deployed, so the air comes through here, majority of it goes, sorry, the minority of it goes through the core, and what gets bypassed will be actually diverted once these thrust reverser sleeves move aft. They've been directed to move aft. They expose this area here, which will then divert the air in a different direction to aft, thus slowing the aircraft down. Controlling the engine, we have different panels. Obviously, we already talked about the master levers. The master levers command the fuel and the ignition to come on. So in an automatic start, just by, if we have bleed air, sufficient bleed air, that's all we need. And the fuel circuit's intact, so the fuel pumps are on the wing. Then by switching this on, if you go in ignition start, you start the engine. That's it. There's nothing to it. Also, we have the ability to manually start the engine, which would be the scenario would be just like a 737 or an older aircraft, where you push the start button. After you've gone into ignition start, you push the start button, and at a maximum N2 rotational speed, you will then put the master lever, this one here or this one here, into the on position. And that will initiate ignition and fuel, and the engine would eventually reach a self-sustaining speed. Okay, at which point you can then switch this off, and you can shut the engine down in the normal way by just putting the master lever back into the off position, and that would shut the engine down by closing the FMU. Okay, so this is to start and start the engines in automatic or in manual mode. I use the thrust levers, the throttle control levers, to regulate the thrust. Okay. 99.9% of the aircraft's life, the system is in auto thrust, because this system is an auto thrust system. So we did talk about patents and stuff in another series, and we talked about the auto throttle is a patent by Boeing, and it's a moving throttle. And when Airbus came along and said, "Oh, I want a sort of automatic throttle system," they said, "Yeah, you can have one, but you can't call it auto throttle because it's a Boeing patent." It was actually a Honeywell patent, but Boeing bought Honeywell, or that part of Honeywell, so Boeing owned the moving throttle concept. So Airbus used the auto thrust system, where the thrust levers do not move during flight. So they are moved from the idle detent to the max continuous or the takeoff detent when we're going to take off. And that's where they're kept until we take off and get into, let's say, 90 seconds after takeoff. There is an indication on the primary flight display for both pilots to adjust your thrust and go into the climb detent. And both pilots will then reduce the thrust levers and put them into the climb detent, at which point the auto thrust will then engage. And it remains engaged. The aircraft will be thrust managed. Okay, whatever the aircraft does, you put anti-ice on, the thrust goes up. Yeah, the RPM goes up, or you go into toga. All exaggeration. All the phases of flight, normal flight, yeah, will happen automatically. The engines, the EEC, will adjust the engine thrust to go higher or lower. Flight idle, higher or lower, with the thrust levers in the climb detent. Okay, and the only time the auto thrust can be disengaged is upon approach at a certain altitude, or usually on touchdown or roundabout touchdown. The pilot will hear his name, retard, and that's his cue to pull the thrust levers and come off the climb detent onto the idle stop. That will disconnect the auto thrust, and the aircraft is already on the ground then, and then thrust levers can be deployed because the aircraft is on ground and the levers are in the idle stop. Okay, so the HCU, the hydraulic control unit, that relay has enabled the operation of thrust reverse, and the hydraulic can then be diverted, whatever color for whatever engine, to the deploy or retract side of the actuator to perform the certain functions, the specific functions. That's the thrust levers. The last one we didn't talk about is this N1 mode. Okay, so remember we talked about the EPA on this engine, EPA being the normal mode of operation. Okay, so if EPA, any EPA parameter was lost, the pressure off the front end of the engine, or the pressure off the back end of the engine, or any other parameter indicating pressure, and EPA could not be displayed as the primary thrust function, I can use the N1 indication as my primary thrust indication, but I've got to tell the aircraft that. I've got to tell all the systems. Okay, so if engine number 2, the EPA parameters were lost, I can put the engine 2 into N1 mode. Okay, so the N1 is the primary thrust indicator here. I would also have to put the other engine. I can't have one in EPA and one in N1. So I will put the other one, and the aircraft can perfectly fly, and the FedEx can use all the indications and controls with N1 as the parameter now. So it's one of the few ways you can tell without having the system display on, because on the system displays, you can see on the primary engine if you're engine 1 or if you're N1 or EPA, you can tell what engine you've got on the aircraft. So a V2500 320 series aircraft will have these two switches on it to be able to resort to an N1 mode. A CFM56 engined 320 series aircraft will not have these switches because the aircraft is already in N1 mode. So if you were ever put in a simulator and you didn't know, or a cockpit, and you didn't know what engines are on this aircraft, blindfolded, somebody wants to trick you, put you in the cockpit, say, what engines has this aircraft got? Immediately, just by looking up here, you can tell if it's got V2500 engines or CFM56 engines. Engine indications. So on the upper ECAM, we have the engine primary indications. Okay. With EPA being the top one, because it's the major thrust indication. And we said the upper ECAM is an engine and warning display. Engine and warning display. And the lower ECAM can be selected, from the ECAM system display selector panel, and shows the secondary engine indications. Thrust reverser indications are indicated that you get a reverse green light when the reverser is actually deployed here successfully, or a reverse in an amber box when the reverser is either deployed, timed out and stayed out, or not deployed at all if there's a fault in the reverser system. These are also things that you'll never see in maintenance. This picture here replaces the engine start valve positions here, which you will also only see during engine start. So if the aircraft's at the bay and the power is on, you will not see the engine start valve positions until you go off the normal with the master switch selector to ignition start or crank. Then you will get the start valve positions indicated, because they're going to be responsible for starting or cranking the engine. Once the engine has started successfully, these will disappear and will get replaced by the nacelle air temperature indications for the remainder of the flight. And obviously, when the engine's shut down, both these will extinguish, and these weren't there anyway.